Brilliant. Thank you so much. So yeah, hi everyone. Hi Andreas. Welcome to Agent Reasoning with Graph World Models. My name's Lucas. I run the MindSynth Agent Lab, and before that was a PhD researcher working on generative models in interactive maps. So in terms of what I'll cover today, I'll give some background, just set the scene. So we've got like a baseline understanding of world models in the context of agents, and then we can focus on how the power of graph representations can be used to leverage like world model concepts and techniques in your applications, hopefully. So just kind of a few things on scope. Obviously, as I said, do a bit of an intro, explain the links between world models and graphs. I've prepared some like toy demos just with like a simple learning algorithm to convey some of the concepts. So I'll go through those as much as I can in the time. I'm assuming that this is really about focused on people who work at kind of the application layer. So this is not to do with like fine tuning the underlying LLM. I'm assuming you're working on the harness, shall we say. But I will look at kind of focusing on how this topic generalizes to non-spatial domains and give you a foundation to learn more. So the key takeaways, if you're building graph-based applications around agents, you're probably quite far along the road to already being able to implement a world model. Actually, it's quite simple to take your existing graph and turn it into a world model. But the big takeaway I want to land today is that even if you're not going to implement RL, you're not going to go down the whole world model rabbit hole. Thinking about your graph schema as if you were going to build a world model is just a really powerful way of thinking about your schema and thinking about your domain, and something I just really recommend. So that's kind of the big takeaway that I want you to get from this. So just to give a quick intro, human agents reason about their environments, about how their actions in their environments can lead to progression towards goals, the ability to perceive and interpret the content and structure of the environment is like a foundational aspect of this, but kind of beyond sort of forming this underlying representation, the ability to reason based on knowledge of the causal effects of actions is really a key skill we have to achieve like multi-step goals in complex environments. So a key thing I want to land today is that world models are not just about spatial context, but obviously you kind of need to start in a spatial context just because it's so inextricably linked. So here, if you imagine like a simple 2D grid world, if we then have a kind of root graph on top of this, although that's kind of derived from the spatial environment, here we can see this kind of compressed topological representation could describe some arbitrary environment. In terms of moving that into something that we could use in a world model, then as you start having agents executing actions and then explicitly tracking observations of the effects of those actions, you can see that this kind of can be tied in the graph directly to, in this case, phenomena like the sunroom, the balcony, but in some arbitrary case, it could be some other aspects of your application. Just kind of give a quick intro. Really like this quote: LLMs learn the structure of language, world models learn the structure of causality. I think that's a nice summary. So if we start to think a bit more about this issue of kind of data modeling and how world models give you a slightly different perspective, consider this scenario. There's a person, a conversation agent, and a memory sub-agent. In this example, how many agents are there? From a world model perspective, there's 3 agents here, because obviously the person, even though they're not in your code base, they play a causal role in the success of your application. So I think that's kind of like a nice example of how this is a slightly different perspective. Another one here, if you imagine this agent in the middle is a conversation agent, what is the agent communicating with? In our schemas or in the way that we talk about things, we might say, well, it's communicating with a person, but often that is not true. It's communicating with the server, which is communicating with the client, which is communicating with the person. So here you might say that the client could be a mobile environment or a desktop environment, and that might have some kind of causal effect in the performance of the agent in its world. So it's kind of just some simple examples, but just to land this idea of a different perspective. So moving on to some of the demos, again, starting with the spatial environment, this kind of simple 2D environment where the goal is just kind of getting to the garden. So here on the left, you see this kind of the actual simulated representation of the environment itself. And then on the right, this kind of state action space that as kind of grows out of like running the agents over this environment. So you can see this is a nice example because in the spatial context, even though you have like a topological structure, the spatial structure sort of naturally emerges out of these kind of agent actions over time. That wouldn't necessarily be the case for your applications, but it's kind of a good starting point. So just to give a sense of what we're actually going to be showing, it's just like a kind of toy learning algorithm where we're evaluating actions using the expected discounted total reward of future trajectories from the current state. So in the demo I'm about to show, we'll have these like rollouts, and all that means is you're just looking at potential futures from the current state and then evaluating what the best course of action would be. So if I show that in a demo, so in this interface, it's obviously quite difficult to explain this quickly in the time. So if I just show a sped up version, see the model is turned off and the agent's just exploring this environment, and you can see how this kind of state action space is just like growing through this like simulation over time. And on the left, you see the rollouts of the predictions. We don't really need to go through this, but you can just see how that grows over time. In terms of like then turning the model on, so if we imagine we've then turned our world model on, and now the agent is able to act based on this kind of causal knowledge about the effects of its actions over time. So this is like the simplest example that you could do essentially, but it just kind of gives us a baseline of how this environment works. So moving on to something that's closer to what you kind of would be used to in in kind of like things that World Labs do, or like the Genie, Google Genie platform, things like that. That's more of a scene-based scenario where you're not just traveling around the routes, but you have to pick up objects, you have to complete tasks within the scene. So to give an example here, again, if the model was turned off and it's very difficult for the agent to actually complete this. I think here it unlocks the door, but never actually gets through to the garden. But again, if you turn on the world model, then it has this it has this ability to think about the causal effects of its actions over time, and it actually completes the task. So if you've got this far in the presentation, you might be thinking this seems like a bit complicated, and what does this have to do with what I work on? But if we think about how you can actually get your graph to do this, is actually extremely simple. There's not a lot of cipher in this talk, but I've provided this as just like a simple example. So here, all of those examples I've just shown you, it's literally just having basically two statistics on a transition edge. And it's quite kind of straightforward to see how you could build out this kind of model on top of your existing schema. So if there's any questions or anything. Right. So moving on to what I call a generalized environment. So a state action space that can be expressed topologically, even if it doesn't derive from a spatial context. So here, the key example is LLM agents, which I assume is what most people are working on if they're watching this talk. I think, yeah, we're doing okay for time, so I'll explain this. So here, you see this kind of state action space represented, and you see how the kind of like white arrows are disjoint the path is kind of broken up. And this is just to kind of communicate how, because we're not in a spatial environment now, this kind of transition of states doesn't necessarily correlate with some like initial topological structure. So here the states are still spilling out over time, even though it might be, say, one agent is calling a tool over and over again rather than moving like across the initial structure. So I just thought it was an interesting thing that shows up in the graphic. But if I go to the example, generalized. So here, in this example, it's like a clinical trial. So the human is a researcher, the human agent is a researcher. He's getting this network of agents to help them create a clinical trial. So the goal here is probably closer to what you guys might be interested in, where it's not a spatial goal, but it's like an informational artifact. And then in this case, the researcher accepting that artifact acts as a reward signal, essentially. So if I show that with the model turned on, so you don't get rollouts for this initial thing just because there's not actually a prediction for what's happening in these nodes. But then once you get through to the agent network, obviously then you start seeing the rollout predictions guiding basically the tool selection. Yeah, and on the left here, see this state action space just kind of growing over time. Just fast forward, you get the idea. And here, yeah, as I said, the human has accepted this this result essentially. So if I go back to the presentation. So in this environment, it's maybe easy to see in this view, we've got the current state, got this view of like the rollouts, some representation of what this environment looks like, a Cypher console, because obviously if you've got all this stored in your graph, you can run all sorts of queries against it. I haven't shown that now, but you can imagine the power of that. This graph view obviously becomes quite complicated very quickly, but it's just to give you a sense of what's happening in the data. So in terms of creating world models for your own domain, then the key thing that I would recommend is to revisit your data model and think through what plays a causal role in your domain, and just kind of take a step back from it, even if you're not necessarily going to be implementing the learning algorithm or anything like that. I think that's just a really great exercise. You can create a simulation environment similar to what I've shown you to test causal hypotheses that relate to things that aren't in your code base. Often, we might instrument a code base to test things which are kind of explicitly testable. If you think about the world that your agent inhabits, lots of things that impact the agent's performance are not in your code base. And that doesn't necessarily mean it's not testable at all. You could still create some kind of simulation environment to look at the causal effects of your agent's actions in your use case. Another thing I would say here is that you may have noticed that some of the things I've shown, if you have an observability platform hooked into your application, then you might already have a system that's kind of generating graphs over like your architecture or over like your agent runs. So it's possible that you might be able to like use the spans or essentially kind of hack the data that you're getting from your observability platform as a basis for building your world model. Yeah, there's a number of tools which you could see how you could sort of hack them for that. Use your professional graph DB understanding to manage the data volume from simulations and learning runs. You could see how, like if I go back to this example, so here, I mean, the it's kind of an odd example, but you can see how easily you start generating like massive amounts of nodes, and it's just from like test runs where you've not really achieved much. So yeah, it's just thinking through like how to manage that data, just using the kind of usual techniques you would do in your work as a graph database engineer. It's just something to be mindful of. But the kind of the main thing I would say here is be mindful that you'd be introducing a kind of a second reasoning engine into your architecture. So usually if you're working with LLM agents or building agents, the LLM acts as the reasoning engine. But then if you have this kind of world model mechanism happening in your harness, then there's this other reasoning engine kind of coexisting with the calls to the LLM. And this is just like a bit of a nuance with having kind of a world model mechanism working alongside your existing system. So we probably do have time for questions, but so maybe if I go through some conclusions and some references and things, and then we could look at if there's any questions from the room. So yeah, concluding, if you're working with agents, world models are for you. This is the main idea I want to get across. I'd say get familiar with the key concepts and take another look at your data model, even if you're not going to take the step into RL. I still think it's massively valuable to have this perspective of agents as things that act. We can observe the causal effects of those actions and think more broadly and more deeply about kind of the world that they inhabit. If you're interested in RL and you already work with a GraphDB, which I'm sure you do if you're watching this, it's kind of quite straightforward to dip your toe in with like a simple experiment. And also, I think just the fact that graph representations as a kind of practical basis for world models will become a bigger and bigger topic. I think it was even mentioned in the opening keynote about how context graphs can be a basis for a world model. It's kind of a natural fit, like so many things are with graph representations. So I think it will be a bigger and bigger topic. And if you're watching this, I think you're early. So here's another quote: "The rabbit hole goes as deep as you want it to, but it's world models all the way down." I partly picked this quote because I really like it, but also this is actually a very recent article, this one by McCormick and DeWitt, not sure how you pronounce, but it's in the references and it's got quite a deep dive on world models, got very, very informed, well thought out kind of perspective. And I'd recommend that if you're looking for some more reading. I won't go through all the references now, but yeah, that's the one I was talking about, computing the uncomputable. There's the URL. And yeah, so that was the main content that I had to go through. Happy to take any questions, or if there's something that you want me to go into more detail in. I appreciate I skipped over a lot of the detail of the demos just because there's a lot there. But yeah, should we look at the messages?
Got some questions in the Q&A tab, if you can pop over to it.
Cool, brilliant, thank you. So first question is, can you explain slide 15 once more? Sure thing. So here I've modeled in the all the examples I've shown, there is an edge called the transition. So, and this transition edge goes from all the phenomena that are represented in each of these worlds. On that transition edge is two values, R mean, visit count. Exactly what these are, I wouldn't worry too much because there's different ways of implementing this. My basic point of this slide is showing that by having simple statistics stored on the edge and then being able to do queries of the form that I show here, you can, this is basically the entire basis of being able to do the rollouts and the like causal predictions essentially. It's literally just storing those stats on the edges and using that as the basis for the rollout. So I hope that answers your question, but feel free to drop a follow up and I'll see it. The second question is, in your slide on creating a world of sorry. Is it a requirement to pre-compute a correlation matrix on the types of phenomena you code from so that highly correlated phenomena are not duplicated in the code? So I don't think it's a requirement. Let me just go to the slide this person is talking about. Creating a world model. I think the way to think about this is that you just need to think very carefully about the data model and what structure you're running the statistics over. If you just have some large graph structure and you kind of embellish your edges with stats and then just like let agents take actions and make observations, then you kind of end up with what you saw in some of the earlier simulations where it's like a random walk and you're just generating loads of data that's not really that useful. So I think, I'm not sure you need a correlation matrix in the context of what I'm talking about, but you need to just think carefully about the schema, really. Thank you. So Desiree asks, is this application on GitHub? So it's not on GitHub, but I'm happy to share it with anyone who's come to the talk. Yeah, I thought it'd be a nice little gift for people who actually came to the talk rather than it just being on GitHub. But I'm happy to share it. So anyone who wants it, you can get in touch with me, and I'll invite you to the repo. You can use it in any way you want. It's just an example for you guys, really. So the last question in the chat is this reinforcement learning? The short answer is it is reinforcement learning, but it's like a very simple, very kind of a simple example of it. Really, what I want to demonstrate with what I've shown here is the fact that it's pretty straightforward to dip your toe into world models if you already work with graphs, and world models are a very useful thing, even if you're not working with spatial data, and are useful even if you're not working with RL. If you want to really go down the world model route, then fundamentally it is a reinforcement learning practice. If you're interested in some of the things that I've shown here, like this can form a basis of then doing like RL on like fine-tuning models and things like that. So this could be like a stepping stone to that. But the short answer is yes, you do need reinforcement learning to make a world model kind of useful in practice. These are all the questions. I don't know if there's anything else anyone wanted me to go over again or cover again. Recommendations for reading references. So if I put the references up again, I assume you'll be able to get access to this presentation again, but here is some references. I'm not sure necessarily these are the best references for world models per se. They were things that I think were relevant to this talk, but it gives you a starting point, I guess. But yeah, I definitely recommend this one, this world models computing the uncomputable. It's pretty detailed, quite fun, and I think it's just a really good perspective on what's becoming a bigger and bigger topic. Lots of people asking how they get in contact. I think you can contact me through the platform, but I'll just put my email address here. That's just the easiest thing. I'll just put my email address in the chat. So, oh, sorry, I'll just do it again. Yeah, thanks. Thank you, Nia. So a few people are asking about the getting your hands on the code. So maybe I'll just talk about what this actually, how to use the interface if some of you are actually going to get the code off me. So here in this top left, you see that there is these are like three demos. So the spatial environment is kind of scene-based one and the generalized version. So that's just a way of toggling between them. You can control the speed of the runs here. You can toggle the model on and off here. You can't quite see here, but you can run arbitrary Cypher queries, and there's some pre-packaged queries just for the examples. In terms of Neo, the way it works is it's just assuming Neo is running in a Docker container. But if anyone has any problem running the code and like getting Neo spinning up in a Docker container or something, then you can reach out to me. Yeah, probably the key thing to know about this is whether this model thing is turned on or off, because that's going to massively impact whether the agents are converging to the goal or not. But yeah, reach out to me and I'm happy to share the code. Any final questions? Don't suppose slides talk will be shared. I'm pretty sure all the slides are going to be on the platform, but okay, so another question. Did you check this approach on how it performs in open source benchmarks? So the idea here is not necessarily to show that this outperforms any benchmark. This is just giving you a sense of how you could start experimenting with world models and using your graph knowledge like within this like emerging topic. So I'm not making any claim here about how it might quantitatively improve your systems. It's something for you to experiment with, really. The learning algorithm that I've used in these examples is like extremely simple. So it's just a kind of a toy example. I hope that answers your question. Someone's talking about the NVIDIA stack. Yeah, absolutely. So this person says, when it comes to world models, I think about NVIDIA AI stack and their movement towards world graphs and models. I think you're seeing, like I said, it was mentioned in the opening keynote of today's conference, and I think it will just become a bigger and bigger topic, both in terms of the kind of more, let's say, traditional 3D environments, and in terms of context graphs and organizational data and all the other places that we have agents running. Amir asks, are you modeling how the agent answers user queries by tracking the sequence of tool calls it's doing? Yes, exactly. So in the case of, if you're looking for basically a user to accept a response that your agents have provided through reasoning with the model, the LLM, yes, exactly. Tracking the sequence of tool calls is like the key thing to understand the causal effect. Obviously, you also need to look at the actual like content that's come back. You might use LLM as a judge or something. But yeah, feel free to reach out to me if you've got more questions. I think we're wrapping up now. Thanks so much for your time, everyone. Really appreciate you coming.